Hello, this is Chapter 5, video number 4. This video is going to be on conditional probability and independence. We have a table over here that says we have three different schools. Let's say this is kind of a larger university. And we have three different schools. We have the liberal arts school, the engineering school, and the health and human services school. And we have multiple grade levels. So we have the total number of students that got A's, B's, and C's in each of the courses. Overall, there are 9,990 grades that are given here. And as I'm looking at this, there's a few things that kind of stick out to me. Well, first off, liberal arts courses seem to be the most popular. Engineering courses seem to be the most difficult. We have 800 students that got a C or below, and then it kind of tapers off with the A's. However, with health and human services, it seems to be the opposite. It seems to be we have the most A's, and then it kind of goes down from there. So let's go ahead and calculate a few separate probabilities here, and I'm going to introduce you to a new notation. So looking at this, let's say that I want to calculate what is the overall probability of getting an A. So probability of getting an A. Well, looking at this, we have total number of A's. I went ahead and added that up. Total number of A's are 3,392, and that is out of my 9,990 courses. And if I divide those, what I ends up with, 3,392 divided by 9,990, that is right around 34%. That is rounded, so I guess I should probably put, whenever something is an estimation, this is the symbol for that. It ends up being like 0.3395. I'm just going to round it to 34%. Now I'm going to calculate a separate probability. Probability of getting an A given that you are an engineering student. All right, now this is a new notation. This is a new notation. So whenever you see this bar, this is a conditional probability. What I want to know is what is the probability that I get an A given that I am an engineering in an engineering course? So for this, my denominator, I am not looking out of my 9,990 overall courses. I'm only looking at these. Given that I'm in an engineering course, what is, oh gosh, that's not straight. But given that I'm in an engineering course, what's the probability that I get an A? Well, looking at this, overall, I have 1,600 total people in engineering courses. And out of those 1,600, 368 of them received an A. So that is my conditional probability. And if I were to divide those out, 368 divided by 1,600, this is at 23%. Now I'm going to write a problem that looks the same, but it is not the same. So probability of engineering given getting an A. Ooh, all right. So in this problem, these two look so similar, but they are not the same questions. This one says, what's the probability that I get an A given that I'm an engineering student? What this one says, what's the probability that I'm an engineering student given that I got an A in the course? All right, so we are no longer looking out of our engineering students. Here's what we're looking out of. We are only looking out of, hey, how many got an A? So I'm looking out of this column. I'm looking out of this column here. Sorry, that's so not great, but pretend that that was well highlighted. All right, so for our denominator here, the total number that got an A, in this university was 3,392. Now, out of those 3,392, there were 368 of them that were engineering students. And if I divide that out, 368 divided by 3,392, that is 0.108. So right around 11%. So these two problems, these two conditional problems, they look very similar, but they are not. All right, so here is one more definition here, and we've kind of talked about this throughout the course, um, but the idea that we have is independence. Now, two events are independent if the probability of one event is not changed by the occurrence of the other. Oh, goodness. How embarrassing. Occurrence. Two R's and an E. All right, so independence. Two events are independent if the probability of one event is not changed by the occurrence of the other. And in Matthew terms, the probability of A should be equal to the probability of A given B. Now, theoretically, in this, grades and colleges are clearly not independent. If they were, these percentages would be the exact same no matter what course you're in. And I just made these up. Maybe it would be, hey, 60% of all people get A's, 30% and 10%. So 60, 30, 10, 60, 30, 10, 60, 30, 10. But looking at this, these percentages are highly affected by what course you are taking. Getting an A is not the same. And the probability of getting an A in an engineering course is not the same as the probability of getting an A overall. So I'm going to go ahead and just fill this in with the values that we got. Let's say the probability of getting an A. If these were independent, the probability of getting an A is the same as the probability of getting an A, given that you're in an engineering course. And certainly that is not the case. Looking up above, overall probability of getting an A is at 34%, but the probability of getting an A in an engineering course, that was all the way down at 23%. So, a few things from this video. First off, notation. These are conditional probabilities. So we are no longer looking at the overall population, we are looking at a specific subset. And finally, independence. Two events are independent if they do not affect each other, if the occurrence of one does not affect the other. And in this case, looking at this event, these are not independent events. These probabilities are not consistent across the school.